Alright guys, here's your video for the beginning of electricity. Just quick stuff to go through, nothing too heavy today. So first we want to talk just about how electricity comes to be. And this we already have talked about the fact that all matter is composed of very small particles called atoms, and the center of an atom is a portion called the nucleus. We know that the nucleus is made up of positively charged particles called protons and particles that don't have a charge at all called neutrons. We also know that outside of the nucleus is a subatomic particle called the electron, which contains a negative charge. Now, these particles have different charges are important because it refers back to this concept of the law of electric charges, which really has three parts. But the two main parts are the fact that charges that are alike will repel one another, and charges that are different are attracted to one another. So if I have a positively charged particle and a negatively charged particle, they'd be attracted. If I had two positively charged particles, they would be repelling from each other, or two negatively charged particles, they'd also be repelling. The third part is actually a statement that objects that have a charge are attracted to objects that are neutral, and vice versa. Now, usually an atom is going to be neutral. This is stuff we talked about long ago. This is because an atom itself has an equal number of electrons with a negative charge and protons with a positive charge, so they end up canceling each other out. But sometimes an atom can lose or gain electrons, and this causes it to become a charged atom, which we call an ion. An atom that has gained extra electrons becomes a negative ion, and an atom that has lost electrons becomes a positively charged ion. We have three different methods of getting an atom or an object to gain a charge. The first of which is friction. This is what happens when you walk around your house and sock feet on the carpet. There's friction between your feet and the carpet, and so some electrons are transferred from the carpet to your feet, or vice versa. And now you have a buildup of a charge on both of those objects. One has gained electrons and become negatively charged. The other one gave up electrons and becomes positively charged. Either way, one object has a negative charge, one object has a positive charge. There's a second way we can charge an object, and this is a process called conduction. This is the transfer of electrons from one object to another by direct contact. So one object has to have a charge. It comes in contact with another object and transfers electrons from a charged object to the other object. The second object may be charged with an opposite charge, or it may not be charged at all. But this requires that one object must start by having a charge, and there must be direct contact between the two. The last is called induction, and this is definitely the most confusing of them. This is what happens when you take an object that has a charge and you hold it up to an object that is neutral. While there's not necessarily a transfer of electrons, and these two objects don't necessarily come in direct contact with each other, the electrons, if I have a positive charged object, the electrons of the neutral object are going to be attracted to the positive charged object, and the protons are going to be shifted away from the surface, away from the positive charged object. So one side of my neutral object becomes negatively charged, and the other side becomes positively charged. The same thing can happen in the opposite manner. If I have a negatively charged object that I hold up to a neutral surface, the positively charged parts will be pulled toward the negatively charged object, and the negatively charged parts, the electrons, will be pushed further away. This just causes one side of a neutral object to be positively charged, while the other side becomes negatively charged. So if we were to look at like plastic wrap, this is the wrap you put on maybe a salad bowl or something if you're going to store it in the fridge to keep the food inside from spoiling. If we were going to look at plastic wrap as an example, the way in which this functions is that first you end up with friction that causes the wrap to get a charge in the first place, and then it's induction that holds that charged plastic wrap to the bowl. As you have, the bowl itself has one side of the bowl becomes negatively charged, and the other side becomes negatively charged, or positively charged. So like the outside of the bowl would become negatively charged, the inside would become positively charged, or vice versa. Now we can determine if an object has an electrical charge. It doesn't tell us whether it's positive or negative, but just that it has a charge with a device called an electroscope. This is an example up here where you would take the object that you suspect might have an electrical charge and touch it to this metal ball at the top, and the electrical charge transfers down this metal rod and causes, there's two little pieces of foil in here, either two pieces of aluminum foil like the one that we have in class, or it can be a metal plate and a piece of foil. But if the object has an electrical charge, both of these pieces will end up with the same charge and therefore repel one another. If an object does not have a charge, there's no charge to transmit, so these two pieces of foil would not be repelled from each other. So again, this is an electroscope, and it only tells us if an object has a charge, not whether it's positive or negative. If we look at just an example of an atom, this is a basic carbon atom. You can draw on your notes packet, and you notice that the number of protons and number of electrons would be the same. So this would cause them to be neutral. The number of positively charged protons, the number of negatively charged electrons are equal, so they cancel each other out, and the overall atom is neutral. So if we're really basic, going to look at the law of electric charges, it says that opposite charges are attracted to one another, and that's what we have up here, some kissy smiley faces. And negatively charged, like charges are going to be repelled from one another. So two negative charges would repel each other, two positive charges would also repel each other. So electricity itself, when we think of electricity, really is just the flow of electrons from one location to another. So electrons will jump from one atom to the next atom to the next atom, and so on until moving through a device that you want to have operate. This could also be in the form of like a lightning strike. You have a cloud that has a buildup of electricity. It transfers electrons from the cloud to air molecules, to more air molecules, to more and more and more and more and more, ultimately reaching, say, a tree, and then through the tree from atom to atom to atom until it gets down to the ground. I will say that the general flow of electricity almost all the time is going to be toward the ground. So the goal of electricity is to reach the ground. Now, when we have electricity that's built up on a single object, we call this static electricity. It can be discharged very, very rapidly. In fact, that's what happens back here when we looked at the lightning strike, is this cloud built up static electricity, and then it goes through this process of static discharge to release that buildup. So this is just can be any number of examples, but this is the sort of thing that makes your hair stand up if you rub a balloon on your head or something like that. That's static electricity. When we use electricity, it's important that we control the electricity as much as possible. So we build these cords like this as a power cord for a computer or TV or something like that. And inside would typically be metal. This serves to be an electrical conductor. We talked about conductors when we talked about heat earlier in the year. In this case, we're talking about electrical conductors. Metal is a good electrical conductor. Water is a good electrical conductor. These are things that will allow electricity to flow very easily. On the other hand, rubber or plastic that we put on the outside of these do not transfer electricity well. These are examples of insulators. Plastic, wood, air, rubber, glass are all examples. Basically, the same conductors of heat are also conductors of electricity. The same insulators for heat are also insulators for electricity. Now, the whole thing we would call a cord that includes both the conductors on the inside and the insulator on the outside. The insulator alone, the conductor alone, we will typically refer to as a wire. So when we use those terms, that's what we mean. Now, there are devices called semiconductors, and these kind of lay right between a conductor and an insulator. They can conduct electricity, but there's some limitations, either in how quickly they can conduct it, or the directions in which they can conduct it, or what they do. Most of the semiconductors that we use are made of the element silicon. So we have a couple that we need to be familiar with. The first is called a diode, and a diode simply acts like a one-way control valve to allow electricity to pass through only in one direction. So like electricity might be able to pass through in this direction, but not in this direction. So the diode itself in the middle acts like a conductor when electricity is flowing this way, but acts like an insulator when electricity is flowing that way. There's a whole bunch of different types of diodes. The most familiar to you is probably an LED, or light emitting diode. When electricity flows through it, it emits light. These are also in a solar panel. The solar cells are examples of diodes as well. There's another type of semiconductor that we need to be familiar with, is something called a transistor. Transistors allow us to amplify the electricity that's flowing through a circuit. So most of the time, these are used in devices that need a lot of electricity or a lot of power, but don't have a lot of power going into them. These are very, very common in pretty much any modern electronics. Notice that all of these transistors are 3 prongs. There's 1, 2, 3 prongs on the end, where the diodes are always 2. 1, 2, 1, 2. So diodes have 2, where transistors have 3 prongs. That's kind of a quick way to, if you see them, to identify whether it's a diode or a transistor. Now, electricity, when it builds up in an object, I've used this term discharge, static discharge, or electric discharge. This is just a very, very rapid release of electrical buildup from one object to another. This is what happens when you go to touch the doorknob and get that shock after you've been walking around in your socks. Lightning strikes are other examples of static discharge. So it's just a very, very, very rapid release of electricity from one object to another. Now, when we use electricity, we need it to be pretty controlled. So we use cords that are made up of wires, metal wires wrapped in a plastic or rubber insulator typically. But we also like our electricity to be able to be available to us on the go. So we have devices that are called cells. Now, most of what you call a battery is actually a cell, like a double A or triple A battery is actually not a battery, it's a cell. Same thing with D or C cell batteries, the button cell batteries that you might find in a watch. These are all examples of actual cells, not batteries. So a cell is really just a singular device that can create an electrical current or a flow of electricity by resulting from a chemical reaction. A battery is simply a device that's made up of multiple cells functioning together. So if you were to ever look at one of these these are like 6-volt batteries, if you were to take it apart, which you should never ever do, it's not safe, but you would see that there's actually 4 different cells inside of there. 9-volt batteries, those little rectangular ones, or 6-volt batteries, these are examples of batteries. Most of your lithium ion batteries are nickel metal hydride or nickel cadmium batteries that you'd find in rechargeable devices. Those are going to be actual batteries where they have multiple small cells inside of them. Now, cells come in one of 2 fashions. There's liquid cells, and these contain literally a liquid inside, liquid electrolytes. Electrolytes really means acids or salts. This is typically sulfuric acid. These are what you'd find in like a car battery or a battery for a boat or a motorcycle or something like that. We don't see a lot of these, and most of the time they already come filled with their liquid and sealed, and you can't do anything with them anymore. But like 20 or 25 years ago, when you bought a battery for a car, you would actually get this bottle of sulfuric acid that you would pour into the cell itself to make the automotive battery, which is it's multiple cells inside, so it is a battery, to make that function. This guy in this picture happens to be pretty dumb because he's wearing sandals while handling sulfuric acid. That's clearly a no-no. Now, most of the cells that you use on a day-to-day basis are actually dry cells, where they have like a paste inside instead of a liquid. That's really the difference. It's just a dry cell is a dry material inside, like a paste or a powder, where a wet cell is a liquid inside, typically sulfuric acid. So when we have electricity flow from one location to another, especially when we're using a cell, there's got to be a difference between the positive side and the negative side in order for electricity to flow through. And we call this potential difference. It's also sometimes referred to as voltage, and it's measured in this unit called volts, and we'll talk more about that in our next video and during our next lesson. But there needs to be able to have this flow of electricity really from the positive side out to the negative side and around. That needs to be able to happen. So if there's not a difference between the positive side and the negative side, then there is no flow of electricity. So when we say a dead cell or a dead battery, what do we really mean? Well, we mean that the battery of the cell no longer has a difference, a potential difference between its positive and negative side. It's no longer a positive side and a negative side. It's just they're the same. So electricity can't flow through the cell anymore, and that means that it's no longer going to function, and we would call that a dead cell. All right, a longer video this time, and I apologize for that, but hopefully everything is clear and ready to go. And then on our next video, we will talk about electrical current and particularly look into some calculations. All right, have a good one.